In this video, we're going to look at radicals and rational exponents. We're going to start with radicals. We're going to try to do a bunch of examples in this video, so pause the video often to give yourself time to think, and then also time to try the problem on your own. So first, just with notation, with radicals, we have what we call a radical symbol. This number up here, we'll put an N here. This is referred to as the index. And we'll kind of talk about that. We'll use that word the most probably of the options. And then what's inside the radical is called the radicand. How you would say this is you would say this is the nth root of A. One common misconception that I want to talk about is something that you pick up when you solve equations using square roots most of the time, is that the square root of 9 is not plus or minus 3, but the square root of 9 is just 3. This is called the principal root. Two of the bigger properties, or the main properties we'll use while talking about radicals in this video, are the product rule. And so if I have the nth root of A times the nth root of B, then I can just multiply what's underneath the radical, A and B. And then the quotient rule is very similar. I can just divide what's underneath the radicals as long as they have the same index. And you can go both ways on this also. You can go left to right or right to left. So all roots must be real numbers for these to hold as well. One thing that is not true, so let's see, we'll put some, write it in red. One thing that is not true is it is not true that the square root of A plus the square root of B is equal to the square root of A plus B. When you add and subtract, you have to combine like terms. This is not true. We'll put some KU colors on that so you guys know it's bad, but do not do that. So let's look at some examples. So when you simplify, the best way to, or the quickest way to simplify is to make sure that you are looking to reduce the fraction first, and then look to take any square roots if possible. So this is a square root because there's nothing here, so it's a 2 there. And so just take the square root of everything. The square root of 144 is 12 because 12 times 12 is 144. A shortcut for exponents is to divide by the index. So 4 divided by 2 is 2. So the square root of a to the 4th is 2. The square root of 9 is 3. And the square root of y to the 6th is y to the 3rd. And then you can say, well, I can also reduce this. So this would be 4a squared over y cubed. And that is completely reduced. And I'm also going to say that all variables represent real numbers and they're all positive. Otherwise, we'd have to think about some absolute value bars, which we won't do in this video. Okay, let's just define quickly some rational exponents and rules and definitions. So if I have the nth root of a to the m power, I can rewrite this as a couple different things. I can rewrite it as the nth root of a and then to the mth power. So I can take this exponent out. Basically, I can do the radical first. It's similar to like when you do order of operations with multiplication and division. Order doesn't matter. If you want to do the radical before the exponent, that's allowed. And this is also written as the a to the m over n power. And so notice that the n, or what's on bottom, comes from the index, and then what is on top comes from the power. So that's a key thing to remember when dealing with radicals and rational exponents. The index is on the bottom, and what's on top is from the power or the exponent. One way I kind of think about it and remember it is an exponent is on, it's kind of on top anyway, right? It's raised to the power, so it's already on top. So when we write it as a fraction, that exponent stays on top. Okay, so we're going to go through a bunch of examples. Pause the video often to give yourself time to think, and also just try these on your own. If you need a calculator, use one. We'll do some with and some without a calculator. So the trick here is just to divide by the index. So we do 16 divided by 2, which is x to the 8th. And then this would be 15 divided by 5, or divided by 3, excuse me, which is y to the 5th. On the negative signs, be careful. It's a common place for error. This is out front, so just the square root of 36 is 6, and the negative doesn't change. Here, this is non-real because I can't take the square root of a negative number. If you want to talk about imaginary numbers or complex, you can. It would be 6i. Because the square root of negative 1 is I. With the cube root of 27, cube root of 27 is 3, because 3 times 3 times 3 is 27. And negative numbers under cube roots are okay because, and this would be negative 3. It just stays negative because if I do negative 3 times negative 3 times negative 3, then I get negative 27. These two make positive 9, and then positive 9 times negative 3 is negative 27. And so any even root can't have a negative underneath it, any even index radical. And then any odd index radical, negatives are fine. Okay, when we simplify numbers, we're going to look for perfect squares, perfect fourths, or whatever it may be, perfect thirds. So here I'm looking for a perfect square that is in 32. So your perfect squares are, 4, because 2 times 2 is 4. So that's there. Good. But anytime 4 is there, 4 times 8 is 32. Check for 16. So square root of 32 is the same as square root of 16 times 2. And then we're going to use our product rule. The square root of 16 is 4, and the square root of 2 is 2. Now, notation really throws people off here. So think about what you're saying. The square root of 16 is 4. It's just 4. So you don't want to put a radical over it because then it would be the square root of 16 is the square root of 4. The square root of 16 is 4. The square root of 2 is the square root of 2. So maybe say it out loud. And a lot of times that helps with getting the notation right. So we need a fourth root. So those you might not know off the top of your head. So let's say, well, 2 times 2 times 2 would be 16. And then, well, that's going to be in there. So 48 divided by 16 is 3. But if you needed to try, you could do, 3 times 3 times 3 times 3 is 81. So 81 is a fourth root. 16 is a perfect fourth. Let's see what we're doing. The fourth root of 16 times 3 is the same thing as 48. And so that's 2 times the fourth root of 3. Here you can simplify first. 50 over 2, because they're both square roots, is just the square root of 25, which we know is 5, because 5 times 5 is 25. And here, take the square root of everything. So it'd be 2a to the third over 3. Remember, you can divide the exponent by the index as a shortcut. Because these problems get more complex when we want to simplify each of these. What I would encourage you to do is don't think of this as one problem, but think of it as 1, 2, 3, 4 little problems. So first, the square root of 32. We just did that. So we know that 4 comes on the outside and 2 stays on the inside because it's 16 times 2. Then think of the square root of x, the square root of x. The exponent is 1. So 2 does not go into 1. And so I cannot take anything out. So it's just x to the first power, or the index. I'm referring to this 2 right here. I divide here. 6 divided by 2 is 3 with no remainder. And so this is y to the third on the outside. And then 5 divided by 2 is 2 with the remainder of 1. Let's write that down. 5 divided by 2 is 2 with the remainder of 1. So if you think about your division this way, that gives you your exponents outside and inside. So it's going to be z squared is on the outside, and the remainder 1 means z to the first remains inside. And we're assuming all the variables are positive. Cube root, make sure you kind of reorient your thinking because you got to think about cube roots. So we have, let's see our perfect cubes for 32. 2 times 2 times 2 is 8. Well, that's in there. If you want to do 3, you're already up to 27. So we can make this, we'll go ahead and write this out in 2 steps. 32 is 8 times 4. Okay, and then once again, think about it as multiple problems instead of one. So just the numbers, the cube root of 8 is 2. That goes on the outside. Cube root of 4 stays inside. 3 goes into 4 one time with the remainder of 1. So c to the 1 and then c to the first remains inside. You don't need to write the ones. I'll put them there just so we can kind of keep track of what I'm saying and doing. 3 goes into 6 twice with the remainder of 0, so there's no w's in there. And then 3 doesn't go into 2, so nothing comes out, and it's z squared inside. Here we need a fourth root that goes into 162. We already said 3 to the fourth is 81. And 81 times 2 is 162. And so go through that same process now with just a fourth root. So fourth root of 81 is 3. And then the fourth root of 2 stays the fourth root of 2. 4 divided by 4 is 1 with no remainder. So we have a to the first on the outside. B goes into 11 twice and be 8 with the remainder of 3. So b to the second and b to the third on the inside. And then 4 goes into 14 3 times. So c to the third with the remainder of 2. 4 times 3 is 12, so there'd be 2 left over. I would pause and think about those exponents on that one. Okay, so when we want to, or one of the reasons rational exponents or these fractions are useful is it allows us to use our rules of exponents. It also helps us to evaluate things if we can go the other way. So with our, let's review our negative exponents here first. This would move it to the other side of the fraction, and it would become positive. And then we can write this as the square root of 16 to the third. Square root of 16 we know is 4 to the third. And then 4 to the third is 64. So this would be 1 over 64. And you can use a calculator for this. It's not likely that someone's going to take your calculator maybe, but if you don't have a calculator, this is a good way to do it. And then also, sometimes it's quicker. It's good to kind of know how the negatives work too. Okay, so this is the same thing just with the negative outside. And so that would just be the same work. Everything is the same except it's negative. Now if the negative's inside though, then that gives us the square root of negative 16 to the third, which this is non-real. And we'll just leave it at that for now. Okay, when we write these in alternate form, so like going back and forth, if this is in radical notation, we want to write it as an exponent. And so the index goes to the bottom of the fraction, and it would look like this. You do need the parentheses to make sure that you know that everything is under the radical or everything's raised to the 1/5. Here, the negative, to get rid of that, you have to move it to the other side of the fraction. And that gets rid of the negative. And then you can write it as a radical, where the index goes on bottom, or the bottom of the fraction is the index. And then it's all raised to the third power. You can use parentheses around here, or you can put parentheses around there, or you could put them both to the third. So, or you might see this. And those are all fine. Cook a few more for simplifying. Your same exponent rules apply. And so like these have the same basis. So you can just add 1/2 plus 1/4. This is, you can find a common denominator, use a calculator, or it's 0.5 plus 0.25 is x to the 3/4. Here, these have a different base, so you have to change something. You could use a calculator, but let's look and see how it can do this differently. 27 is the same as 3 to the third power to the 1/4. So if we change that, now they have the same base, and I can use my exponent rules. When I'm up high, multiply. So that's 3, to the 1/4 times 3 to the 3/4. And then now I can add exponents, and 1/4 plus 3/4 is just 1. And so that's just 3. Okay, so we can put all this together to simplify some pretty nasty looking exponents. There's a lot of different ways to approach this problem. I think it's best to maybe simplify what you can inside the parentheses first. So these a's are the same, and so you can subtract exponents, or think of it as moving it, the a to the negative 3m to the bottom. But if we subtract, you want to start with the bigger exponent. So 9m minus negative 3m is 12m. Okay, so let's just do that. And it'd be on bottom because that's where we started our subtraction. Okay, now we're going to raise everything to the negative 1/3. Okay, so when we up high, we multiply exponents. And when we get the negative, I don't really like flipping the fraction because it doesn't flip the fraction. But in this case, everything raised to the negative power. So a lot of things will move. But let's actually just multiply each exponent. So it'd be negative 27 to the negative 1/3. And then this would be b to the negative 6n times negative 1/3. And then a to the 12m times negative 1/3. Okay, let's make sure you can see that. Now simplify. So negative 27, this negative doesn't matter. It's just the problem's negative. It's not going anywhere. But this is I can evaluate this. So 27 to the 1/3 power is 3 because it's the cube root. And the negative exponent means it needs to move to the bottom of the fraction. So that 3 is going to move down there. The whole thing's negative, so let's just leave a negative up top. Here, multiply these exponents, and you get a positive 2n. So the 3 and 6 reduce. So you don't have to move the b. And then here when you multiply, you get a to the negative 4m. But I don't like negative exponents, so we move that to the top, and it becomes a to the positive 4m. And then usually you would put the a variable first. So let's rewrite it. Oops, I forgot a 2. So just be careful with that. A lot of negative signs to mess you up. And then the last one we'll look at in this video, raise everything to the 1/2 power. So it's 9 to the 1/2 x times 6 times 1/2, and then y times 2 times 1/2. And you might be able to do that step in your head. 9 to the 1/2 is the same as the square root of 9. So that's 3. And then x to the third when I reduce, and y to the first. Okay, good luck with radicals and rational exponents, and reach out if you have any questions.